Hey, what's up guys? Welcome back to the channel. In this particular video, I will explain the coin change problem. This problem is again a standard DSA problem and frequently asked by many companies guys. So make sure you stay tuned till the end of the video. Starting with the problem statement, so it says that you are given an integer array coins of size n which represents different denominations of currency. Along with this, you are also given an integer sum. Your task is to find the number of ways you can make sum by using different combinations from coins array. Okay, now guys, it says that assume that you have infinite supply of each coin and you can use any coin as many times as you want. So let me explain the problem with a given example. So we are given an array. This array contains coins of three denominations, which is 1, 2 and 3. Basically, this 1 means that this is a coin of 1 unit, and this 2 means that this is a coin of 2 unit, and 3 basically means a 3 unit coin. And our task is to make sum of 4 unit by using these coins guys, and I can use any coin as many times as I want. So what I can do is guys, I can choose this particular coin 4 times in order to get 4 unit of sum, right? So I can choose 1 1 1 1, and this is going to give me 4 unit of sum. The second way that I can have is I can choose this one two times, so I can have 1 1. After this I can choose this 2, right? And this is again going to give me the sum 4 unit. After this, the third way that we can have is I can choose this one, and then I can choose this 3, right? And this is going to give me 1 3, and again the sum is 4 unit, right? And one more way we can have is we can choose this particular 2 two times. So I will have 2 2, and 2 plus 2 is nothing but equal to 4. So again I have 4 unit of sum. So you can see that there are total 4 ways which can give me the sum 4, right? So the answer is going to be 4 for this particular example. Now guys, I hope you have understood the problem statement well. So let's talk about the solution now. Okay, so I have written one example here, quite similar to the one given in the problem statement, but this time I have taken smaller value for sum so that it becomes easier to explain for a smaller example. Guys, after looking at the problem, the first approach that comes to my mind is we can try out every possible way, right? And after this, we can simply sum up all the ways which gives me sum equals to 3. And this way, I'll be able to get my answer, right? But the question is how we can try out every possible way? This is the question that you are gonna ask me, right? So guys, in order to understand this, I want you to pay attention here. I have written all the ways which are going to give me the sum 3, and we are going to derive some observation from these ways. Starting from the first way, can I say that in this way I am including 1, then again including 1, then again including 1, right? After this, for the second way, can I say that include 1 and include 2 and don't include 3, right? After this, for the third way, can I say that include 3 and don't include 1 or 2? This basically means that for every element in the array, I have two options. I can either include this element or I can ignore this element, right? This is the approach that we are going to follow, guys. Let me explain how it works using the dry run. So first of all, I'm going to draw the array here. The array that we have is 1 2 3, right? And guys, I am going to start from the first element. Initially my I is equal to 0, and I is going to move to every possible element of this array, and for every element we have two choices. We can either include it or don't include it, right? And we are going to keep track of the sum till now using the current sum variable, which is initially equal to 0. And the moment we get current sum equals to 3, we need to stop here because we have got our answer, right? We have got one of the ways, and our task is to return the total number of ways, which is 3 for this particular input, right? You can see here. Now guys, question is what happens when we include an element? So whenever we include an element, so our current sum is going to increase by that particular value, so 1, right? Our current sum will become 1 now. And what happens to this particular index I? So one thing is sure guys, when we ignore this element, then I is going to increase because we are ignoring this element, right? So for this case, I will simply point to this value, right? And my current sum is going to remain same because we are not including the current element, right? But what about this particular case? Whenever we include an element, then we are going to remain at the same index. Why? This is the question why. Guys, the answer is, see, we can include the same element multiple times, right? So when I include this one time, then there is a possibility then I can include this one like multiple times as well, right? So I am going to remain at same index. After this, again for this one I have two choices, right? And First choice is include, second is don't include. So when I include, then my current sum is again going to increase. Now my current sum will become equal to 2, right? And I'm going to point to the same index that I have. This is what include basically means. And talking about the don't include, so in this case I'm simply going to move to the second index. So I have 1 2 3 and I will move to this 2, right? And current sum is going to remain same for this, which is 1. After this, for this one again I have two choices, either include or not include. So when I include, guys, then what happens is I will get current sum equal to 3, right? And I'm going to point to the same index. And what about this case? For this case I have current sum equal to 2, right? And when I include, when I don't include this one, then I'll simply move to the next index and current sum is going to remain same. So current sum equal to 2 for this, and now I'm pointing to this element. What about this case? So for this case I have again two options. I can either include it or ignore it. When I include it, then the current sum will become 3, right? Because current sum is 1, and when I include 2, so current sum will become 3. And for this, current sum is going to remain same, which is 1. And now I will point to the last index, which is 3, right? Okay, what about this case, guys? For this case I have two options. I can include this 2, so I will get current sum equal to 2 and 1 2 3. So I'm pointing to the same index, right? And I can ignore this 2, so I'll simply come to the last index which I have, and 1 2 3 I'll come to this index. Our current sum is going to remain same, which is 0. For this again I have two choices. I can either include it or ignore it. When I include this 3, so I'm going to remain at same index, which is 3, right? And current sum will become 3 now. For this, current sum is going to remain same, and I will come to out of this array, right? So now I'm out of this array and all the elements are done, right? So guys, this is about the dry run. I'm not going to complete this dry run. Of course some elements are left here, but I'm not going to complete this. I think this much is enough to explain the idea to you guys. You can see that I'm able to get my ways, right? This is one of the ways, this is again one of the ways, and this is again one of the ways. So there are total 3 ways, right? So whenever I explore to include and don't include, so I have to add up all the possibilities, right? So guys, I have to add up all these possibilities. Now I hope the dry run is clear to you guys. Talking about the idea behind the implementation, so let me talk about the idea, guys. I have written a general array here. This array is going to take some coins C1 C2, somewhere Ci in the middle, and then we have Cn at the last, right? So let's say this Ci is basically going to represented by the index I, right? So I have two options for this. I can either include and don't move, or I can don't include and move, right? So what does this mean? Let me explain, guys. So when I include, then my I is going to remain same, and this current sum is going to increase, right? So my current sum will become C plus C of I, right? Or I'll say coins of I. This is how I am going to increase. And what about this don't include? When I say don't include, then my I will increase and current sum will remain same. So this is basically going to represent my current sum. Guys, this is what include and don't include means. Now talking in terms of implementation, so we have a function here, and this function is basically going to take 4 parameters. I have I, which is going to represent the current index I, right? After this I have array, so this is going to represent this coins array. After this I have C. What does this C means? This C basically means current sum, and this sum is basically the target sum, right? Now guys, see what happens when we include. So whenever we include, let's say I'm pointing to this I, let's say I'm pointing to this I. So when I include this element, then my current sum is going to increase, right? My current sum now become equal to 1, and target sum is 3, right? So now I need two more sum in order to get my target, right? So can I say that now this is my target and I have to find this particular sum in this particular array? So guys, this is again a similar problem. This means that this is going to be a recursive approach. I'm going to call the same function in order to solve the problem, right? I'm going to call the same function. So how I'm going to call the same function? See, I have two options. Option A says that include, right? So when I say include, then I'll simply call the same function, and it is I comma uh, I comma array. Then I have C plus C of I, right? Or array of I, and then I have sum. This is first way. And the second way says that solve, and then I have here I plus 1, and then just don't increase the sum, right? Because I'm ignoring the value. At last I just need to return A plus B. And what about the base condition? When I'm going to stop, so whenever my current sum becomes equal to the required sum, then I need to stop, right? So if my current sum becomes equal to the required sum, then I'll simply return 1. Return 1 basically means that I'm going to increase my ways by 1 because now I have got one more way, right? After this, guys, there is one more condition. Let's say this I moves from left to right, right? This is what happens. So when this I will become out of bound, then I need to stop, right? This means that if my I becomes equal to length of array, right? At this point I need to return, and I'm simply going to return 0 because we have not found out any way and my elements are over now, right? So I'm simply going to return 0 for this particular case. I hope you have got the idea, guys. Now let me show you the exact implementation because there are some problems with this implementation. Let me discuss one of the problems. One problem is, guys, whenever our C plus array of I becomes greater than sum, then it is going to throw an stack overflow error. Let me explain why. So for this dry run, guys, see here, you can see that we have current sum equal to 2 here, and when I include this 2, then my current sum will become equals to 4, right? My current sum will become equal to 4, and we are not going to handle this particular case because we don't have any condition for this case. So we will check this particular condition. Only after this we will call this particular line, right? We are going to call this particular function. Let me explain this particular thing in detail. So guys, this is the exact implementation that we are going to use. This is how we are going to handle that particular condition. Like, if our current sum plus current coin that we have is going to give me the sum which is smaller than equal to target sum, only in that case I am going to increase my current sum, right? Only in that case I have these two ways, and if this is not true, then I'll simply call or I'll simply skip the element that I have. Guys, this is the recursive approach that we have. Now I hope the idea behind the recursive approach is clear to you. Question is, what is the time complexity of this approach, guys? The time complexity of this approach is something which is exponential. Let me explain why. So there are n elements in the array, right? 1 2 3 up to n. There are n elements. So guys, for every element we have two choices, right? For this element I have two choice, then for this element I have again two choice, and like this I have two choices up to n. So this is nothing but 2 raised to the power n, right? So these are the total number of ways. So the total time complexity is going to be O of 2 raised to the power n. This is the time complexity of the approach, guys. So now we are going to optimize this particular approach so that we can run this approach for larger inputs as well, right? This is what about the optimizations. So now let's talk about the optimal approach. So I want to show you the dry run in order to explain the problem with the recursive approach that we have. See guys, this is the dry run that we have, and all these are sub problems. If this is a problem, then all these are sub problems, right? And this is what optimal substructure says. That optimal substructure basically says that every solution to a problem is basically dependent on the solution to sub problems, right? Once we have found the solution to these sub problems, then we can simply add those solutions, right? And then we will get the final answer. I hope you understand this, guys. Now I'm going to pick a random sub problem. So let's say I have this particular sub problem. So for this sub problem, guys, we have current sum c equals to 2, and we are pointing to the second index, right? 1 2 3, and I'm pointing to the second index, and I can find the same subproblem again in the same like dry run, right? You can see that again we have the same subproblem, c basically equal to 2, which is our current sum, and my pointer is pointing to the second index, right? So my question is, guys, once we have solved this problem, then why we are solving the same problem again and again? So you can see that we are solving the same subproblem again and again, right? So guys, this is something which is going to increase the work that the CPU or the system needs to done. So this is something which is going to increase the time complexity. We have to avoid solving the same problem again and again. And guys, this is something that we say overlapping subproblems, right? So till now we have figured out two main things. The first one is optimal substructure, and the second thing is overlapping subproblems. You can see here, guys, and whenever we have these two conditions in our recursive approach, then we can say that the problem that we have is a dynamic programming problem, guys. I hope you have understood the intuition behind the dynamic programming. So now, as we know, we have a dynamic programming problem. So there are two ways to solve. The first one is memoization, and the second one is tabulation. So let me start with the memoization approach first. Guys, it basically says that you are going to optimize the recursive approach. This is basically optimization over recursive approach, right? And how we basically perform that optimization. So whenever I solve a sub problem, then I'm going to store that particular problem somewhere in an array, and after this, before solving any problem, I will look for the solution in the array. So let me take the same dry run in order to explain. See guys, this is a sub problem, right? This is the sub problem that we have. So what I'm going to do is I'm simply going to solve this problem, and after this I'm going to store this in the array, right? And before I solve this problem again, I'm going to look in this array whether I have already solved it or what. If I have already done this, then I'm simply going to pick the solution from the array itself, right? And this is going to take O of one time. This is how we can access any index in the array, right? So guys, now see, we are simply going to optimize the recursive approach. I have the recursive approach here, and I need an array in order to store every subproblem. So let's say this array name is DP, because DP makes more sense here, because DP is basically representing a dynamic programming array, right? So guys, I need to store every subproblem. See, each subproblem can be uniquely represented by a value of I and current sum, right? Because these are the changing values. So I can use I and current sum pair in order to represent any values. We have two values, right? So guys, this means that we can represent any problem with a 2D array. So I have a DP array which is a 2D array, and this is going to represent any subproblems like this. These are indexes, these are indices which are going to represent the sub problem, right? So guys, I'm going to store the sum, I'm going to store the solution in this particular index for each sub problem. So let me modify the recursive code. I'm simply going to write dp of I and current sum is basically equal to this particular value, right? This is my answer. Before I return this, I have to store this. So I'm simply again going to store here as well, dp of I comma sum is equal to this particular answer, right? And guys, now as I have stored the solution, to multiple subproblems, so before solving any problem, I have to check whether I have already solved it. So I'm simply going to check if dp of I comma c, okay, is something which is not equal to null, right? I have to represent, guys, I have to represent this null or unsolved problem by some value. So let me fill this particular array by -1. Let me represent a unsolved problem with -1, right? So if this value is not equal to -1, this means that now my problem is solved, right? This value is not equal to -1, so I simply need to return dp of I and current sum. So I'll return dp of I and current sum, right? This is how, guys, we can perform memoization. And now the time complexity of this problem has been reduced. Let me talk about the new time complexity. So see, guys, any subproblem is not going to go out of bound for this particular DP array, right? So this means that I'm not going to solve this problem more than I cross whatever is my current sum. What is the maximum value of I that we can have? So maximum value of I can be equal to the size of array, right, which is equal to n. And the maximum value of current sum can be sum, because if it is greater than sum, then we are already handling this particular case, right? So this value can be equal to sum. So we are not going to traverse more than n cross some subproblems, because if any subproblem is outer than this, then we are going to handle that particular case, and that is going to be out of bound for this DP array, right? So total complexity, time complexity for this problem is n cross sum, and space complexity is again the same, guys, because you can see that we are using a DP array, right? And this array is again going to occupy this much space, and additionally we have some recursion stack space as well, because this is a recursive problem, right? So again the complexity is going to be increased by recursion stack space. So this is about the space complexity. Now guys, I hope you have understood the memoization approach. So let me show you the code quickly. This is the code that we have, guys. You can see that we have the recursive function, and we are using a DP array, and this DP array is basically going to perform memoization, right? And you can see the recursive approach as well. We can figure out the recursive approach from this approach only, guys. You just need to return the DP part from this, right? This is the Java code, and this is the Python code. Now guys, I hope everything is clear related to the memoization approach. So we are going to talk about the tabulation approach, guys. Now guys, let's see the tabulation approach. Okay, so I have written the recursive code here, and guys, tabulation approach is all about converting this particular approach into something which is independent of the recursive call. How we do this? So I have written the DP array here, and guys, we know one thing, that every subproblem to this particular solution belongs to the DP array only, right? This means that we can represent any subproblem with DP of I comma C. And you can even see here that we have different values for I and C every time we come into this particular function, right? So guys, this means that this answer can be represented with dp of I comma c, and when I say solve for I plus 1 and c, then this is basically dp of I plus 1 and c, right? After this, when I say dp of I and c plus answer of I or array of I, my bad, so I'll simply write dp of I then c plus coins of I or array of I, right? So guys, this is the recursive relation for the dp array that we have. Similarly, for this we have a dp of I comma c equals to a dp of I plus 1 and c, right? For this particular case, like when this condition is not true, and c basically belongs to the column of this particular array and I basically belongs to the rows of this particular array, right? But the question is from where to start. Like when we say traversing this dp array, so there are four options. I can start from top left, or I can start from top right, or I can start from bottom left or bottom right, right? And this is the question that many of you ask me, that hey, how to get the intuition for tabulation approach, like from where to start traversing the dp array? This is very frequently asked questions, guys. So let me explain. Tabulation approach is also known as bottom up dynamic programming. Bottom up dynamic programming. So unlike we do in recursive approach, we start from the problems itself, then we move to the base cases, like, right? So in bottom up dynamic programming, we start from the base cases and then we move to the bigger solution, right? Bigger problems. So this is something that can give us the idea. See, for the base case, my c is equal to the sum and I equals to the n, right? So in this particular array, when my I is equal to n, so I'm talking about the last row, and my column is equal to sum, so I'm talking about the last column. So this means that I have to start from this place only, right? And after this I will move to this particular cell, and this is going to give me the answer. So dp of 0 and 0 is going to give me the answer for the main problem that we have, right? And even you can see that when we start from recursive approach, so we start from 0 comma 0, right? Because this is the value for I and this is the value for c, and this is the solution to main problem that we have. So guys, this is the similar idea. See, we are going to start from this particular last cell. So for I equals to n, then I is greater than equal to 0, then I plus plus, I minus minus, right? Because we are moving from last row to the first row. And similarly for c, for the column, we have for c equals to sum, then c is greater than equal to 0, then c minus minus, right? And guys, now I know dp of I comma c is basically going to represent every sub problem. So first of all, I have to start with the base case. If my I is equal to n or my c is equal to sum, in that case I can say that dp of I comma c is equal to 0, right? Okay, no, there's a mistake here, guys. See, both the values, answer for both the condition is different. So I'll say that, okay, if my c is equal to sum, then my dp of I comma c is equal to 1. And if my else, if this condition not true, only then I will come to this condition. If my this condition not true, so I'll say if my I is equal to n, then written, okay, then dp of I comma c is basically equal to 0, right? After this I have to write this condition. So I'll simply say that, okay, else, inside this I'll write, first of all, let me remove this, guys. Now inside this I have to write, if my c plus coins of I is something which is smaller than equal to sum, in that case I can write this particular line, right? And if this condition is not true, then I'll write this particular line, like dp of I comma c is equal to dp of I plus 1 comma c, right? But guys, always make sure that when you write I plus 1 c, then this is something that can go out of bound, right? So we have to handle this condition as well. Similarly, in this particular line also, we have to handle this particular condition, right? We are not checking if our I plus 1 is smaller than c. So guys, this is about the tabulation approach. I'm going to show you how we can handle this particular condition, I plus 1, this condition in the code only, right? Before that, let's talk about the time complexity. So here the time complexity is going to remain same, O of n cross sum, right? And the space complexity is again O of n cross sum, because we have like we are using this dp array, right? And this is something which is independent of the recursive call. This is very important, guys. Let me show you the code now. So this is the code, guys. This is the tabulation code. You can see that we are just making a table here, which is my 2d dp array, right? And after this I'm filling out value, and I'm using ternary operator in order to handle the I plus 1 condition, guys. I plus 1 is not out of bound, right? Similarly here as well, you can see that Java code as well. In the Java code I'm using this condition. Okay, this is the Python code, guys. In Python code we have a syntax something like this. this is the Python code. My bad. Like I missed out that this is the Python code. So this is how we handle the condition in Python. Like we can write if else in a single line. After this, this is the Java code, again ternary operator in order to handle the condition. Guys, this is all about this video. I hope you have understood everything that you should know about this problem, right? Thank you.